All right, thank you guys for coming at 4 p.m. on a Sunday. Today I'm going to talk to you guys about a new technology for gas chromatography. The technology was actually born out of university research and was developed and commercialized by Activated Research Company, which is a company I co-founded back in 2014. So before I get started, can I get a show of hands in this room so I can tailor the talk of how many people use gas chromatography? Okay, awesome. There's a lot of you guys. Okay. So for this talk today, I want to go through some of the problems with traditional gas chromatography and flame ionization detection. And then I'm going to go into this Polyarc reactor, which is a catalytic reactor that you add onto your gas chromatograph. And you're able to convert all of your compounds to methane so that the detection sensitivity of your FID is the same. So I'll go through that. And then I'm going to go through two big examples of using this reactor technology for, number one, quantifying compounds that are traditionally invisible or very low detective sensitivity in the FID. And then secondly, quantifying compounds, big mixtures, without using calibration standards. So I'll go into why that may be and why that's not heresy. So our product solves a big pain point with a lot of people who use gas chromatography. If you're Paul at the University of Minnesota, what he was doing was he was pyrolyzing cellulose. So he's researching renewable fuels, renewable chemicals, compounds. And to do that, he wants to pyrolyze cellulose to produce all of these chemicals. Well, the problem with that is when you look at a GC chromatograph with FID, you see hundreds, if not thousands, of different peaks. These peaks could be a variety of different things that happened when you pyrolyzed this cellulose. For him, this was a nightmare. How am I going to quantify all of this? How am I going to close my carbon balance? He was doing kinetic studies to try to figure out where this carbon was going. There's a lot of oxygenates in here, a lot of heteroatoms, so there's a lot of variability in the response factors. So traditionally, how would someone go about analyzing this? Well, they'd take hundreds of calibration standards, right? For those that they couldn't find, they would have to synthesize, or they'd have to pay a lot of money to purchase them. Or some of them might not just be able to synthesize or purchase. And in that case, you're kind of up a creek. Hundreds of calibration curves to try to get accuracy up. So they invented what is known as the Polyarc reactor, which is a chemical reactor that converts everything coming out of that chromatograph, coming out of that column, into methane before it gets detected by the FID. So here's a picture of the commercialized Polyarc reactor. It's a stainless steel 3D printed cartridge, and it sits on top of your GC. Here you can see it behind a flame ionization detector on a common gas chromatograph. And what happens inside of this tiny reactor is a sequential two-step reaction. So first, your analyte comes into this reactor. It gets combusted in a combustion chamber to carbon dioxide and combustion byproducts. And then that stream, you add hydrogen to it and you reduce it, and you form methane with larger than 99.9% conversion. So there are proprietary catalysts in this reactor, and with the help of thermodynamics, we're able to ensure that we get above 99.9% conversion for every single analyte that we send into this device. And that's critical for enabling analysis, quantified analysis without calibrations. So I want to stress that this is not a methanizer, although the closest analogy I can bring to you is that of a methanizer, because it is a reactor that goes into your GC. And it's not a methanizer for three main reasons. One is you're converting all of your molecules, not just carbon monoxide and carbon dioxide, all of your molecules to methane. It also uses capillary flow technology, and it is resistant to poisoning by sulfur, chlorine, fluorine, nitrogen, other heteroatoms. So here's a diagram of a traditional gas chromatograph and then a GC with a Polyarc on top. So this Polyarc reactor, you can see you inject your components here, A, B, C, to be generic. They get separated in your column and they go up into your detector. However, on the right side, what you form is methane as you're going through your column, and that's instantaneous. And you can see your chromatograms change. So in this case, if A, B, and C were equal carbon molar amounts, on the left side, without a reactor, you might have different areas of your peaks because you have a different sensitivity of that FID to different molecules, right? On the right side, everything's been converted to methane, so the peak areas would be the same on a per carbon basis, right? So it's a pretty simple concept. Everything's being converted into methane before it reaches the FID. FID burns methane the same, you get the same peak areas on a per carbon basis. Now this is critical because this enables us to do quantification on a wide range of different molecules without calibrating for differences in sensitivity of the FID, right? So to illustrate this, I want to go through a few examples where we drastically increase the sensitivity of the FID. So we'll start with CO and CO2. Those, of course, can be handled by traditional methanizers, which are nickel catalysts that convert those to methane. And what we see, if you put CO and CO2 into a GC with an FID, for CO you see nothing. And that's because if you look at the FID, if you send CO into a flame, you're not going to burn that CO and form these CHO ions, which are what we're counting when we're using a flame ionization detector. So you're not going to form those electrons from that ion that you form. You will with methane, you won't with CO2, and you will with other linear alkanes. When you instead convert everything into methane before you analyze with the FID, now we see an equal sensitivity for CO and CO2, also for ethylene and ethane. So on a per carbon basis, these areas are all the same. Because our conversions are larger than 99.9% to methane, we have detection sensitivities that are very accurate and very high. So you can also look at other compounds that are traditionally very difficult to analyze with an FID. Formic acid, for example. If you send that into an FID, there's a very tiny peak here, and you can see there's about an 8% or 0.8% detection on the FID relative to methane. Whereas when you convert it to methane before, you have linear response and identical sensitivity to that of methane or any carbon species. We could also look at formaldehyde, and the story is very similar. Very little detection in the FID, much higher when you're converting everything to methane. Right, and again, our response factors are all 1 because everything is methane. So there's a lot of other compounds as well. You can think of perchloro, perfluoro compounds that aren't sensitive in the FID and can be converted to methane using this method. Here's just a bar chart comparing some of those response factors. So if you're looking at CO, CO2, formamide, formaldehyde, and formic acid, those detection limits are very low, if not infinitesimal. Whereas with the Polyarc reactor converting everything to methane, now the response factors are all the same and your detection limits are all the same. So those were some examples of analyzing molecules where they're traditionally difficult to look at with an FID. We can also look at any and all molecules for larger analyses, which is really what this technology was designed for. So here's a snapshot of some of the molecules that have been tested. You can see a lot of them have been derivatized. And they represent a number of different industries, including pharmaceuticals. We've also got foods and fragrances, cosmetics, commodity chemicals. You saw examples that relate to natural gas. So really a wide scope. As you know, anything you can put into a GC could be analyzed with this technology. So I want to give an example of a complex mixture. The funny thing about testing this technology to show that we don't need standards is that I need a standard to show that it works, that you don't need a standard. So I'll show you that real quick. So here's a calibration standard you can purchase from a commercial vendor. And it's got a number of different compounds with different functional groups, different carbon numbers. And what you see, this is with the Polyarc reactor attached to your GC. And we see nice sharp peaks, as you would expect for a GC. And when we look at the measurement error on an average percent, when we're just using a response factor of 1 for all of these different types of compounds, we see that that measurement error is about 2% on average. And again, that was just one sample, no calibration at all. If we instead do a single point calibration with just an FID now, we remove that reactor, we do our calibration to find our response factors. We can see that our measurement error is more like 4.5%, 5%, and we've done 8 samples now to calibrate for all 8 of those compounds. We could also, if we're really bold, do a 5-point calibration. And again, this was using 32 different samples to figure out the response factors, slope, and intercept. And our error gets a little bit better, but you can see with that many samples, we're still about the same, if not better, with the Polyarc reactor with no calibration at all. And that's because we're converting everything to methane, and you're avoiding any of those errors associated with creating standards, handling standards, letting them sit around, those sorts of things. So we can say confidently that our error is comparable without any use of standards. So this is pretty neat, and we should all be excited we don't have to make standards anymore and use them. Another example that I want to look at is pesticides. So pesticides are neurotoxins. Obviously, we want to know if these are in our food or our soil. And there's about 16,000 pesticides known, about 10,000 pesticides approved by the EPA. So analyzing this breadth of compounds and trying to quantify these with standards is really an insurmountable task for anyone. There's about 64 pesticides that are banned by the EPA but still show up in food, so DDT comes to mind. So we took a study, and this work was actually done at the University of Minnesota by a colleague who's sitting in the audience, and they looked at 22 organochlorine pesticides using this Polyarc reactor technique. So here's a comparison of using the reactor versus not using the reactor, and this is just to show you that the chromatograms are the same. So you're not affecting your chromatography when you put this device in there, right? It was designed for GC. It has specially engineered flow channels that are capillary and that allow these small analytes to be analyzed with sharp peaks, right? And you can see here the response factor for a wide range of different pesticides are essentially 1 within our ability to detect. So we can analyze now the breadth of 10,400 approved pesticides. We can quantify them if we know their identity, or we can quantify them just on a carbon basis even if we don't know their identity. And that's without any calibration. So with that, I want to thank you all for attention, and I will definitely take any questions. Please come see us. We're at booth 3222. We are co-exhibiting with Pace Analytical. So thank you for your attention.